from the University of Pennsylvania, formerly an undergraduate at Rutgers University, who in the junior took my experimental math class. He has found a long way, and now she's talking about very interesting generalizations and proof of conjecture of the Zaleski-Zeilberger conjectures and theory. And as usual, if you behave, you're invited to come to dinner as the usual place, Evelyn, at 6:45. Evelyn on New Brunswick in Eastern Avenue. But that's the condition for coming. You have to tell me right after the talk. I'll be standing here taking names. So I know how many people to reserve. Thank you. Go ahead.
Thank you guys for having me. What I'm going to talk about is joint work with János, Komlós, a Rutgers person, and Gábor Tusnády. And this was all, as Doran said, inspired by stuff that he had done with another Rutgers person, Zaleski. So the main topic is ST cores and distributions of ST cores, but it's really like a long excuse to tell you about some really cool probabilistic tools that I got to use to solve this problem. So first, definitions first. An ST core is an integer partition whose Ferrer's diagram that's an N has no hook of length S or T. So, for example, my notes go. 73221 is an integer partition of 15. It's a weakly decreasing sequence of positive numbers, and they add up to something. That's the number we're partitioning, or the size of the partition. And then we associate to this a Ferrer's diagram, which is just a collection of left justified boxes so that the ith row has lambda I boxes. Okay, so the bottom row has length 7, 3, 2, 2, 1. And each cell in this diagram has a hook. So this cell, the hook is everything above that cell and everything to the right of that cell. And the hook length is just the number of boxes. So this hook has length 4. So if I write all of these down, you can see there's no 5 and there's no 7. You can say the statement lambda is a 5, 7, 4. It's also true that there's no 5 and there's no 8. This is also a 5, 8, 4, etc. So these are not mutually exclusive sets of integer partitions. And theorem, due to Jacqueline Anderson from 2002, is that if S and T are coprime, there are only finitely many. ST cores. And she proved a lot more than that, actually. She gave this really beautiful lattice paths characterization of these partitions. Maybe if we have time at the end, I'll tell you about it. I hope I get to. So just as a little example, very little, there are only 5 3-4 cores, and they look like this. The empty partition, that counts. 1, 2, 1, 1, and 3, 1, 1. You can see there's no hooks of size 3 or 4 anywhere in there, and I claim that this is all you can do. Any other partition will have a hook of length 3 or 4. And these objects come up in other areas of algebraic combinatorics. But what sort of prompted this whole study of distributions of them is that Drew Armstrong in about 2011 made this really nice conjecture about the size of an average, the average size of an ST core. And then following that, Doran asked, well, the average is just one facet of a distribution. Why don't we ask about whole distribution? And that's what led to this study. So we put a statistic on this set, the very natural statistic of size. So what number are these partitions partitioning? And we ask about the distribution of this statistic on this set. So forever, from now to infinity, whenever I talk about S and T, I'm going to assume they're coprime. So the first surprise is due to Doran and his computer. Okay. And that's that this distribution is not normal. So usually when we ask a combinatorial question, what's the distribution
It's
of...
not asymptotically normal.
Yeah, I'm going to say all the details of what that means.
Of
This
course
is
it's not normal.
this is a fuzzy sentence, and
It's a
in
discrete distribution.
yes, this is not approaching normal.
Okay.
Usually, when we ask about something finite, some combinatorial thing, then in the limit we get the normal distribution, or maybe we get some other familiar thing like an Airy distribution, something like that. But not only is this distribution not approaching the normal distribution, it's not approaching anything else that's familiar in the world of combinatorics. It's quite a weird distribution that you get. Okay, so what specifically am I talking about? What do all these words mean? So more precisely, we think of for each pair, S and T, coprime, we get a random variable, yst, which is the size of a random ST core. And by this I mean chosen uniformly at random. So this finite set, pick one at random and see what the size of it is. Then I'm going to look at the normalized cumulative distribution function, which we'll call little fst, of some variable x, and that's the probability that my variable is at most x standard deviations above the mean. So this is going to look like some kind of a step function that for a while, when x is like a big negative number, this thing on the right side is negative, and so there's no cores with size less than -1. So this probability is going to be 0 for a while, and then it's going to make some steps up. Every time we see a core of the appropriate size, we'll go up, 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 until we get to 1. And so at some point, then it'll be 1 forever. At some point, well, this should be more like this. At some point, we'll have seen all the cores, and then forever it'll stay 1. So we have this discrete thing. And now, if you fix t minus s to be something, and let s go to infinity, you get some point-wise limit. Because these are normalized, so they're always going to be kind of centered and scaled appropriately, so we can see at each point what the limit of these function values are. And you'll get some kind of a curve, which goes to 0 on the left, goes to 1 on the right, and it's monotone in the middle. Call it fx. And what Ekhad-Zeilberger are saying is that f of x is not the cumulative distribution function for a standard normal random variable. Now, if I say it like that, it doesn't sound very, very surprising. Why should it be this one curve and not any other? but it is a very common distribution in life and in combinatorics. So we're still a little surprised. And if we have that mindset now that why would anything be normal anyway, then you have a second surprise coming to you. And now this is from Zaleski in 2017. There's strong evidence that if you look at the distribution of size among SS plus 1 cores, so we're fixing that difference between S and T to be 1, with the additional restriction that all the parts are distinct, then this is approximately normal. But out of all the limiting curves you could get, somehow we end up with the capital Phi distribution here. So just for that quick example, maybe I'll just do it underneath here. If we're looking at these 5, 3, 4 cores, right, only 3 have distinct parts. Namely, this one with no part, this one and this one with a single part, but not these two, because they both have the part 1 repeated. They both have 2 rows of length 1, so that's not okay. So that's the distribution we're talking about. So the main result here is that we prove this statement that Zaleski gave us really strong evidence for, but we prove actually something a little stronger because instead of just making a limit statement, we give some kind of control about how quickly this limit converges. Okay, so we're going to fix S, and we'll let x sub s be the random variable size of a random SS plus 1 core with distinct parts. And we'll let mu and sigma be the mean and standard deviation of this random variable. And we'll let f of x be this cumulative normalized thing. So that's all just notation. Now I can tell you the actual statement that we're going to prove. So the theorem from the 3 of us is that whatever s you pick, as long as it's a positive integer, you take the sup over all real numbers x of the difference between f and capital Phi. Then this is on the order of 1 over square root s. So this is a statement about every single s, and this capital O thing means there is an absolute constant, C1, which doesn't depend on anything, x, s, nothing. It's just a number like 1,000. So that for all s and x, this difference is bounded by C1 over square root s. Okay, so this is...
Can you come up with a specific C1?
So one of the tools that we use has this formulation that like there is an absolute constant. So if you wanted to figure out what C1 is, you would first have to go back and figure out what that constant is. It's doable.
So you know how to do it.
We didn't do it.
It's okay.
So I promised you tools. So now that we know what we're trying to prove, it's time to tell you one of the tools we're going to use to prove it. So, someone's coffee sitting here. So, the first big tool is called the combinatorial central limit theorem. So in general, the phrase central limit theorem usually means I'm going to say that something is asymptotically normal. And the original form of the CCLT was from 1951 due to Hofting. What we're going to do here is a little more modern. It's a little more precise. Yeah, so we're going to take a matrix. And our random variable is going to be denoted S sub A, and that's when you look at a random diagonal of this matrix. So when you compute determinants, you look at products of things like this, and then you add them up with pluses and minuses. So we're looking at some random determinant, picking a permutation in SM uniformly at random, and then adding up all of the elements on that diagonal. Okay, and this is the variable that's going to be asymptotically normal once we have all of the little niggly notations down. Okay, so we're going to have mu A and sigma A be the mean and standard deviation. And we're also going to have this extra notation, Aij with a little dot over it, for just a little renormalization. So we take the actual entry Aij and subtract the average of the row and the average of the column, and add back in the average of the whole matrix. So just some renormalization. And now we're ready for the theorem, which is from 1984 and due to Bolthausen. Okay, so he said, and here comes the unknown constant. There is an absolute constant. Called capital K, so that for any matrix with any variance at all, we get this bound. We're going to look at that cumulative normalized thing again, compare it to capital Phi, and our bound here is going to have K. It's going to have those Aij dot thingies and the standard deviation and the size of the matrix all in it. This is a precise statement for any matrix of any size. It's just that if you don't take a sufficiently big or sufficiently varying matrix, then this bound is not going to be very useful. All right, but this is a precise statement, true in general, as opposed to the original version of the combinatorial central limit theorem, which is the limit statement. That's why we need this newer version. So how does this come into play? Sounds cool, but what does it have to do with cores or anything else that I said so far? Well, for that we need to look a little closer at the combinatorics of cores. So here's the part where I would love to go into Jacqueline Anderson's bijection and tell you all about why this statement is true, but for now I'll just tell you the statement. Proposition, this is due to Stroud from 2016. Okay. A partition lambda into distinct parts is an SS plus 1 core if and only if the biggest hook, which is going to be the number of parts plus the longest part minus 1, is at most S minus 1. Okay. So we can get rid of all of this hook business and just look at the length and the largest part of the partition and get a criteria. So we kind of shortcut all of that weirder combinatoric stuff at the beginning. Okay, idea. What happens if we fix the length of lambda to be something, K? Well, then the statement says a partition lambda into K distinct parts is an SS plus 1 core if the largest part is less than or equal to s minus k. And since that's the largest part, I'm just saying all the parts are less than or equal to s minus k. So this gives us a really nice correspondence. So let's look just at a quick example. If s were 5 and k were 2, Straub is saying, what are all of the 5, 6 cores into 2 distinct parts? All you have to do is pick 2 different numbers less than or equal to 5 minus 2. So our cores are going to be 2, 1, 3, 1, and 3, 2. And what I'm going to do is associate each one of those to a simple little 0, 1 vector. I just put 1s at position I when there's a part of size I. So this is clearly a bijection based on what Straub said, and that's going to tell us, for instance, how many of these there are. Right? From this we can see the number of them is s minus k choose k. And also we can get the size of the original thing back by taking the corresponding vector and doing the dot product with the vector 1, 2, 3, up through s minus k. Because that means that a 1 at position I is going to contribute I to the size. So it's a really nice, simple characterization then once we've fixed k. And so, we're going to let xsk be the size of a random s plus 1 core into k distinct parts. And we're going to have the mean mu, k, and standard deviation, sigma k, theorem. This thing is normal. As long as k isn't one of the extreme boundaries, we get this kind of normality statement that we had before. The difference between a cumulative distribution function and the capital P function has some bound. And the proof is we're going to apply the CCLT with A equals the outer product of the vector with k1s followed by s minus 2k zeros, and that vector 1, 2, 3, all the way up to s minus k. So when you do this, and then you take a random diagonal, whichever columns end up in the first k rows, that's going to be like, which numbers did you pick to be part of your partition? So we're going to be very naturally generating these guys. It's just with a little multiplicity because it doesn't matter what happens in the 0 rows. So it's really natural to see the correspondence between this variable and the SA we get from this A matrix. And then everything else is just calculations and plugging in stuff. Very boring.
So this is stronger than mere asymptotic
Yes.
normality. It's more quantitative.
Yeah, this tells you sort of how quickly you get asymptotic normality. And you can see here when k is close to 0 or close to s over 2, it converges really slowly. And that's a mess. We are going to actually not apply this theorem for every k. We're going to only apply it in a small range. and we'll see that the other k's don't matter. So the corollary that we're actually going to use is for k between s over 4 and s over 3. Then the suit thing that we get has a much nicer bound, which we didn't optimize, but one upper bound you can get is 1,000 times k divided by the square root of s. So this is why ultimately the theorem we end up with is going to have an order 1 over square root s thing in it. Because inside this range, that's what we're going to get, and then outside the range will show that it's negligible, it's not important. All right, so what have we said so far? This variable that we're really interested in, the xs, is a mixture of variables which are all approximately normal. When you mix normal distributions together with different parameters, usually you don't get something normal. So just a pictorial example where I use the regular distribution, not the cumulative one. If you had a bell curve with a negative mean, and then you mixed it together with a bell curve with a positive mean, with weights 1/2, 1/2, the thing that you get would be very much not normal, right? It wouldn't even be unimodal. So at this point, it's sort of surprise number 3. The things that you're mixing together are normal, and somehow you do it in a way that the output is also normal. Very weird. So in order to achieve this, we're going to have to be careful about how we mix these together. So that's why we're going to end up with another tool. So as I mentioned before, we had that characterization. Actually, I'm just covering it up. We had this characterization with 0, 1 vectors, which makes it clear that that the number of SS plus 1 cores with k distinct parts is S minus k choose k. And this sequence has a nice generating function that's well known. Looks like this. A pretty Z analog of the formula for the Fibonacci numbers. Instead of square root 5 everywhere, we just have square root 1 plus 4z. Who can have a nicer generalization? So at z equals 1, we see that the number of SS plus 1 cores with any number of distinct parts, that's going to be the sum. So when z equals 1 is just one of the Fibonacci numbers. Okay, so what we're going to imagine is that we have another random variable called w, and it's going to take value k with probability s minus k choose k divided by fib s plus 1. Another way to generate the exact same distribution would be take a random SS plus 1 core with distinct parts and output the number of parts. Right? This is the proportion of those cores which have k parts. So we have this random variable, and in order to generate a random SS plus 1 core with distinct parts, first we'll generate a random size, a random length, a random number of parts with w, and then we would use the x